All right, welcome ladies and gentlemen. This is video number 2 in our acid-base unit, and this is a pretty hefty video. This is a real important one, so I hope you are paying attention. And we're going to talk about conjugate acid-base pairs. What are they, and how can we figure them out? And how can you tell if a salt, an ionic compound, is acidic, basic, or neutral? Because yes, we can have acidic salts, even though they might not look to be acidic from just a first glance. And yes, we can have basic salts, or they can be neutral, and we got to figure out how we know that. So first up is conjugate acids and bases. This is a really important definition. We're going to be using this concept not only this unit, but the next unit as well. So the term conjugate in general means pairing. If you think of it really crudely like a conjugal visit, that's a pairing of people coming together. If you think about bacterial conjugation, that's about bacterial reproduction. So conjugate in this context means pairing. So a conjugate base, it's what remains after an acid donates a proton. So it's what do you have left after your acid has given away its proton. So for example, if you have HA, your acid, and it donates a proton, and you're left with A minus, the A minus would be called the conjugate base of HA, because it's what is left after the HA has donated a proton. A conjugate acid is the same idea, just for a base. A conjugate acid is the thing that is created when your base acts like a base, meaning after your base has accepted a proton, what is the thing that you now have left? So if we have our base plus water, remember we need to include our water in our dissociation reaction, the water will donate a proton to the base. We'd be left with Hb plus the hydroxide ion. Well, what did our base, the B, turn into? It turned into Hb plus. So Hb plus is the conjugate acid of B. And this diagram that's right on the top is showing this in the format of a full-blown reaction. So we have the chemical formulas here, and then we just have a picture here. So notice that we have HA in the formula, and then we have our A, and then we have our hydrogen here. And then water, because we're oftentimes acid-base reactions, they're almost always happening in water. And we obviously have our oxygen, and then a hydrogen, and then a hydrogen. And what's happening in this reaction? Well, the hydrogen is being transferred from the HA to the H2O. So we turn into H3O plus. So I've gained that, right, we have the water has an additional hydrogen than what it started from, and then we're left with just a minus over here. So again, the HA has lost its hydrogen. So this entire reaction actually contains two conjugate acid conjugate base pairs. The HA turned into A minus. So A minus is the conjugate base of the acid HA. Together, we say that they're a conjugate acid-base pair. HA and A minus together are a conjugate acid-base pair. And then the water and the H3O plus. Well, the water was acting as the base. So the H3O plus is actually the conjugate acid of the water. So H2O and H3O plus, they're another conjugate acid-base pair. There's a really crucial point about conjugate acids and conjugate bases that you're going to have to sort of keep in mind as we continue throughout this unit, and that's right here. A conjugate acid-base pair does not actually react with itself. HA does not react with A minus. So for example, if you consider HA and A minus, I mean, they both have A, and you had a quote-unquote reaction, well, what would you get if the proton transferred? You'd get A minus and H. You get the exact same thing, right? You get the exact same thing that you started with. This is not a chemical reaction. So conjugate acids and conjugate conjugate acid-base pairs, they don't react with one another. It's always things that you'll find on opposite sides of the chemical reaction. Just like we found HA as a reactant and then it turned into a minus, right? It's on the other side. And then the H2O was the base and then it turned into H3O plus. So it turned into its conjugate acid. So they're always going to be on opposite sides of the equation and they don't actually react with one another. The term pairing is not referring to a pair of things that are reacting together. Instead, it's saying, what did your acid become after it reacted? What did your base become after it reacted? With this in mind, we can write formulas for conjugate acids and conjugate bases. So if I have this question, what's the conjugate base for each of the following acids, and then there's a whole bunch of acids, in order to figure this out, it's really just thinking about, what do acids do? Well, what do acids do? Acids donate protons, which means that they get rid of hydrogen ions. So if we want to figure out the conjugate base, that's the thing that's left after your acid donates a proton. We are simply going to remove a proton from each of these things. And if you remove a proton from perchloric acid, you take away an H+, you're left with ClO4 with a negative charge. That is the conjugate base of perchloric acid. Now H2S, threw this one at you for a reason. It's what happens when you remove a proton. A proton, one proton, because remember, polyprotic acids, this is a stepwise thing. They don't lose both of their hydrogens at once. So I'd only take away one hydrogen from H2S. I'd be left with HS, and the charge would simply be -1. HS minus is the conjugate base of H2S. Not the sulfide ion, not S2 minus. You only take away one proton at a time. Likewise with pH4 plus, I'm only going to remove one hydrogen ion, so I'm going to be left with pH3 with a neutral charge. pH3 is the conjugate base of pH4 plus. And the bicarbonate ion, take away a hydrogen ion, you're left with the carbonate ion. And that is your conjugate base right there. And then we're going to do the same thing with we want some conjugate acids. Now, if we say conjugate acid, then that means that the thing must have been a base. It says it right there. But yeah, if I asked for a conjugate acid by definition is a thing that came from a base. So what do bases do? Bases steal protons. Bases accept protons. So now instead of taking away a hydrogen, we're going to simply be adding just one proton to all of these suckers. So the cyanide ion, that's definitely a base. You add a proton onto it. What do you get? You get HCN. You get cyanic acid. The sulfate ion, the charge is -2, but we're not going to add 2 protons. We only want to add one, just one at a time. We don't want to fill it up. It's a stepwise process. Remember, our polyprotics, they only lose or gain one hydrogen at a time. So HSO4, now the charge would be -1 because I've only added one positive. So I go from -2 to -1. Water, add on a proton to water. What do you get? You get the hydronium ion, and then the bicarbonate ion, HCO3 minus, you add on a proton to that, H2CO3, and just pointing out the bicarbonate, that amphoteric substance, right, it can do both. Now, how do you know if something is an acid versus something is a base? This concept of conjugate acid-base pairing is actually going to be directly related to acid-base strength. And there's this critical relationship right here. The stronger an acid is, the weaker its conjugate base is going to be. This chart that's on the left here is actually showing this. We have relative acid strength here on the left and relative conjugate base strength here on the right. And I first want to point out the extremes of this. So basically a very strong base is shown down here and a very strong acid is shown down here. This would be your strong acid, these would be your strong bases. A strong acid has an incredibly weak conjugate base. So this would be HCl and Cl minus. So what do I mean when I say its conjugate base is really, really weak? What that means is that the conjugate strength is so weak for these strong acids and strong bases that it's negligible. Well, what does negligible mean? Basically means it's non-existent. Non-existent, right? So chloride is not a base because it's the conjugate base of hydrochloric acid, and hydrochloric acid is a strong acid, so its conjugate is ridiculously weak and essentially incapable of acting like a base when it's in solution. But we have this whole other middle section right here. What if we don't have a strong acid or a strong base? What if we have a weak acid? Then what does that mean about the conjugate strength? Well, look over here. A weak acid, its conjugate is also weak, but it's a weak conjugate base. Well, okay, what does that mean? What is that saying? It means that the conjugate bases of your weak acids are actually functional bases. They're just not strong bases. They are weak bases. So strong acids, their conjugate bases are non-existent. They're neutral. They're ridiculously weak. But weak acids, their conjugate bases are actually functional bases. And you may or may not remember all the way back in September when we talked about how do you identify an acid. How do you know if it's strong or weak? It's a really simple thing. It's like, you know you have a strong acid if it's one of the 7 strong acids that you memorized back in September, right? You memorized them, right? So that way you know if it's not one of the 7 strong, you know it must be weak. And then we said, okay, well, what are the strong bases? Well, here are the strong bases that we memorized. And how do you know if you have a weak base? And I said, well, that's actually a more complicated discussion. We're going to have it later in the year. Guess what? Later in the year is right now. This is how you know if you have a weak base. This is how you identify a weak base. Is it the conjugate base of a weak acid? If so, it is a weak base. HCl versus acetic acid. HCl is a strong acid. Acetic acid is a weak acid. What are the conjugate bases of these suckers? Well, the conjugate base of hydrochloric acid is chloride. The conjugate base of acetic acid is the acetate ion, C2H3O2-. These are both conjugate bases because they are both what the acid turned into. However, chloride, being the conjugate base of a strong acid, is neutral. But the acetate ion, because it is the conjugate base of a weak acid, is in fact actually a weak base. This is how we will now identify weak bases, if it is the conjugate base of a weak acid. Putting this in words, rather than just the diagram. A strong acid completely dissociates, 100% dissociates. It's going to have far more products than reactants, meaning you're not going to actually have any of your strong acid molecule left, right? All H plus and A minus, no HA. And it will yield a negligibly weak conjugate base. What does that mean technically? It means technically that the conjugate base of a strong acid is a much weaker base than water. Water is kind of like our middle ground where we say if something is a stronger acid than water, then it's an acid. If something is a stronger base than water, then it's a base. But realistically, there's actually more detail that you can get into, which you might get into in college. So the conjugate base of a strong acid is a far weaker base than water. So for us, that essentially means that it's neutral and not capable of acting as a base. A weak acid, on the other hand, will incompletely dissociate. It will have far more reactants than products. So I like to sort of write it this way, that if you had a mixture of a weak acid, it would be almost all HA, that's why that's really big, and only a tiny little amount of H plus and A minus. And again, the weaker the acid, the stronger its conjugate base. So that means the conjugate weak base from a weak acid is actually a stronger base than that of water. So it can actually function as a base. But what you have to remember is that just because you have a weak acid, that actually gives you a weak conjugate base, not a strong conjugate base. Not strong like the 100% dissociated, like, because it's still not going to completely dissociate. So weak acids give you weak conjugate bases. Strong acids give you non-existent conjugate bases. And this is exactly what we're going to use to figure out if a salt is acidic, basic, or neutral. And I'm going to go through two examples with this. I'm going to go through the ammonium chloride first. So I give you this salt and I say it's ammonium chloride. Cool. Is this an acidic salt, a basic salt, or a neutral salt? The key to doing this, there's a process. This salt is not going to stay together in solution. So when you put it in water, it won't be ammonium chloride. Instead, it's going to be ammonium and chloride. And the way that we evaluate whether or not the salt is acidic, basic, or neutral is to consider each of these ions in the salt separately. Consider the ammonium, figure out if ammonium is acidic, basic, or neutral. Consider the chloride, figure out if the chloride is acidic, basic, or neutral. And then from that put together, see if the salt is acidic, basic, or neutral. And then what we want to do is think about the conjugate of each of these. So we're saying that these two things, ammonium and chloride, these are the conjugates of what? What acid or base gave us ammonium? What acid or base gave us chloride? And I would hope that you can sort of see this in your head, but if you have trouble visualizing the acid or base that it came from, there's a little trick that you can use. You can add either H plus or OH minus to get the acid or base that it quote unquote came from. Basically, when I say it came from, it means that's the acid or base that it's the conjugate of, the acid or base that you would have started with that would have then generated that particular ion. So you're not going to add both, so we have to think, are we going to add hydrogen to H plus or hydroxide to NH4 plus? And we want to add OH minus because, you know, charges, right? We're not going to add a positive to another positive. We get bad things when that happens. So you can sort of think as NH4OH, although it's actually NH3. But you can think of this as this is the conjugate of the ammonium. And then likewise, chloride, add either H plus or OH minus. Well, we want to add H plus because negative, right? Positives, negatives, they go together. So HCl. And then think, so this is our conjugate. That's our conjugate. Then think, is this a conjugate acid or a conjugate base? Well, you know, ammonium / ending in hydroxide. This is a conjugate base, which means that ammonium must have been a conjugate acid, right? The ammonium would have, quote, started as NH4OH, and then if it dissociated, it would have generated the conjugate of NH4 plus. Likewise, same with the HCl. You want to think, well, okay, HCl, that's an acid. You put an H out in front. So that's a conjugate acid, which means that this is a conjugate base. Then you want to think again about these things down here. Are these strong or are these weak acids and bases? Well, NH4OH / ammonia, neither of these are on the list of strong acids that we're going to memorize. So, sorry, strong bases. So this is a weak base. Well, what does that mean if the conjugate acid is coming from a weak base? It means that ammonium is actually a weak acid. Weak acids have weak conjugate bases, and then vice versa is also true. Weak bases have weak conjugate acids. So because the ammonium is the conjugate of a weak base, which we figured out by thinking about the ions, we know that ammonium must actually be acidic. Likewise with the HCl, we determine that it's an acid, so is it a strong acid or a weak acid? Duh, this is hopefully the one strong acid that you know at this point in the year. Memorize the rest of them, guys, seriously, come on, memorize them. So it's a strong acid, so what does that mean about its conjugate base? It means that its conjugate base is actually neutral. So we have this ion, which is a weak acid, and we have this other ion, which is neutral. So what does that mean about ammonium chloride? It's an acidic salt due to the ammonium. And we know if we put ammonium chloride in water, the pH is actually going to go down, which is very true because the ammonium is capable of donating some hydrogen ions. Now I'm going to do one more example just so we kind of get this process, hopefully do it a little faster. Sodium bromide. So what do we want to do to figure out if it's acidic, basic, or neutral? First of all, split it up. Na plus Br minus. Evaluate each thing individually. Then think, these ions are the conjugates of what other ions? What acid or base would you have started with that would have generated then these particular ions? And again, the trick to that is add H plus or OH minus. So I'm going to add OH minus to this. I get NaOH, and I'm going to add H plus to this, and I'm going to get HBr. So these are the conjugates. Now think, these are conjugate acids or conjugate bases. Well, hi, this ends in hydroxide. That's a conjugate base. And oh, look, this starts with H out in front. That's a conjugate acid. Right? So you identified, okay, that's a base, that's an acid. Which means then, if this is the conjugate base, then this must be a conjugate acid. If this is the conjugate acid, this must be the conjugate base. So you're kind of identifying that right now. Then you're thinking strong or weak for these suckers. Are those suckers strong or weak? Sodium hydroxide, that is a strong base, yo. HBr, also a strong acid. Okay, well, if you have a strong base, what does that mean about the conjugate acid? It means the conjugate acid is neutral. If you have a strong acid, what does that mean about the conjugate base? It means the conjugate base is neutral. Right? Strong acids and bases have non-existent, negligent conjugate acids and bases. So sodium is neutral, bromide is neutral. It means that NaBr is a neutral salt. You put sodium bromide in water and the pH will not change. The pH will stay right exactly where it started. So this ability to identify weak bases based on conjugates and then use that to figure out if your salt is acidic, basic, or neutral, this is a really big skill, and we're definitely going to be practicing this in class.